And so let's see. We talked about the initial value problem, and throughout this courses, we learn the Wooler's methods, Taylor's methods to apply the to do the approximations here. And one question about the thing is that, so once we get the methods here, this is the numbers we get. This is the Taylor's methods of the order 2, and this is just one table, one approximations to the solutions of one IVP problem, initial value problem. And we only get the approximations at certain point because we set the step size as the h equals 2.2. And as you can see, this is the time interval 0 to 2. We are solving the initial value problems this is the initial value problem we are solving. And the time interval is set it in as this way, the 0 to 2, and the step size is 0.2. And as you can see here, we have 0.2 step size. And in this table, this is the results of the approximations by using the Taylor's order 2 methods. And we only get the values at 0.2, 0.4, 0.6 with the increment size of 0.2. But what happens in between this, 0.4 and 0.6? And what about the values at 0.5 or any points in between? So we can use the numbers generated by the Taylor's methods or Wooler's methods or other methods, and then you can just do some interpolations to get the values in between. And this is the knowledge you learn in the 104 4A. So I have given you some things on the lecture notes, and I'm going to give you the guide how to do the linear interpolation and the Hermite interpolations here. So one question on the textbooks is, okay, we got the numbers at the 1.2 and 1.4. And these are, so this is the, when the time, I believe you have already understand some things about this part throughout your homework, but we mention it again, and then to double check if you have a correct understanding here. So here we have the Ti, and then there's one part is the T equals to the 1.2, and then there's another part here, another time is equals to 1.4, and so the question is that, and then what about the values at the 1.25? So we want to get approximations to this point. And what about the T, at the node point? At the node point 1.2, and the Y evaluate at the 1.2, it's actually approximated by that WTI. And the WI here, WTI here, and then the WTI here is corresponding to the 3.19134A, and by looking at the table here. And so for the Y 1.4, and then it's approximated by the W value, and then the W value here is 3.748645. So the things in between, you can either use, so here, this is the time 1.2, and this is the time 1.4. This is T-axis, and then this is the Y-axis, and then if you have the value here, this is the Y W value here at the 1.2 time, and this is the W here at the 1.4 time. And you can either use the linear interpolation here, and then to get the point values at the 1.25. And I would like to remind you of the linear interpolations equation. You can use other formula for this one as well. So, but if you have 2 points, so this is something from the 104A, linear interpolations between 2 points. And let's say we have 2 point A and YA, so and the B and YB. These are 2 points, and then we want to do the linear interpolations between them. And the linear interpolations polynomial looks like this. I use the px to represent it. It's x minus a, and then b minus a, and yb, and plus the b minus x, and then b minus a, and then ya. And this is the linear interpolations between these two points. And because here we want to do the interpolations for the 112. So for examples, here we have the interpolations, and we have 2 points here, and then the t, this is the 1.2 point, this is the first component, and this is second component for the first point. This is the first component, and this is the second component for the second point. And we want to do the interpolation here. And the 1.25 is located in between this interval. And so what we are doing here is to plug in the value, all the value we have here, and into this linear interpolations polynomial. And so at the end of the day, you got this. And this is the x is just the 1.25. 1.25, and then minus the a is the 1.2, and b minus a, and what's the yb? Yb here, it should be the another value that is the 1.4. The value is at 1.4. So this is the things. And so here we just have, this is our x, this is our a, this is our b, this is a, and so this one is just the yb. And next is the next plus c, b, it should be the 1.4 again, and then x is the 1.25, and then divided by 1.4, 1.2, and the ya, it should be the values at the time 1.2, but it's the approximation, and so we got the 3. So here this value should be the 3.19134a, and this is how we calculate the values approximations at the y equals to 1.25, and you can do all the you can approximate the values in between any interval, subinterval here by using the linear interpolation here. But people think about this. Okay, this is one way we can approximate it. Actually, you can do use any interpolations you learn in 104A to do the interpolation and to get the values in between. You can use any values, you use any interpolations, interpolations, the Lagrange interpolations. You can use any methods to do the interpolations here. And as you can see from the 104A, and you will see this is just the basic version, and one better version of the interpolation is the Ermites interpolation. It could have the same point value at the node point, and it could also have the same derivative values at the node points. And the way we calculate the Ermite things is to, so I would like to remind you of the equation, what we have. So I'm going to talk about this again because some of the people's in our class just forgot what is the Hermite interpolation. And the things to calculate the Hermite interpolations is quite easy. The idea is complicated, but the way to calculate the Hermite interpolations is quite easy. So what you need to do is to get the table. Oh, it's a big table, and because we are interpolating both the value, nodal point value, and the derivative as well. So we duplicate the point here. So for his samples, we have the nodal point A, and then we duplicate to A here, and then we have two entries. We have two rows for A point, and then this is the another nodal points in between, and then we duplicate it and we duplicate it because one rows we have to interpolate both the value, nodal point value, and the derivative. So we have two entries here, and so the second columns are the F values evaluated at those points, and the third columns. So we have the first derivative here at the x0, and this is the divided difference between 2 points because these are 2 different points, and then we can do the divided difference, which means that we are going to use the subtractions between these 2 values and divided by the subtractions between these 2 values. And as you can see here, for this column, the first one, we cannot do the divided difference because at the denominator, we have the same value, and then this will become 0, and then this is not well defined. So this one should be the first derivative at this point. And as you can see, we can persist looks like this, and then do the final difference for the third column, for the fourth column here, and so on and so forth, and then create a table. And with this table, and then we plug into, this is the coefficient here. The coefficients value, we calculate it here in this table, and we plug in the values to this formula, and then we get the Hermite polynomials interpolations formula. And so what we need to focus on to create this formula is just the first components in each column. So these are the values we focus on, and this table is very useful, and I have these tables at the at everywhere in the midterm exams review last quarter, and then I have throughout these courses, and then I copy and paste again at this table. This is quite useful. But let us get back to what we have in this example. We are doing the Taylor's methods for the IVP problem. And what we get here is 2 points, and then we want to ask the question again, what is the Y values evaluated at the 1.25? So what we do here is to use the Hermite interpolations. This is another way to get the interpolations, to get the approximations at the 1.25 value. So this is what, once again, this is a question, and then how to get the approximations at the points 1.25. We are going to use the Hermite interpolations to do it here. And let's calculate the table first. The table here, we have, so let's just follow this table and then create the columns here. And for the Z here, we have, so once again, I would like to remind you of the Hermite interpolations. We have to duplicate the point here. So for the Z here, we have the first one, we have the 1.2, and then the second rows, we also have the 1.2. And for the third rows, and then we have the component 1.4, and we duplicate it, and then we have the 1.4 here. And for the values evaluated at that point, so instead of the points we got the exact value, we replace the exact value with the approximations value. So the second column should be the approximations value because we don't know the true solution. So here we have the approximation here, y1 at the 1.2, the approximation is this value. So the FZ here, it should be FZ, and then it should be the 31.9134A, and this is the same. And for the Y, evaluate at 1.4, and then we use the value here. This is the approximations value from the Taylor's method, and we duplicate it. Duplicate the value here. Okay, this is the second column corresponding to what we have here. And for the third column, and then we should be very careful because we don't know the true solution. Once again, we don't know the true solution. And for this one, we don't know the derivative as well. So what we do here is, so this is not F, this is the Y corresponding to our question statement. And this is the Y value. And what we did here is, so this is Y prime Z. So this is the first divided difference. But the first divided difference here, we actually not using the exact Y derivative here because we don't have the information at hand. So what we did here is a little bit complicated because this is the equation. Let's go back to our question statement. This is the example 5, and then the question is solving the IVP problem. The Y derivative equals to Y minus T squared plus 1. So which means that, so the Y prime T equals to the YT and then minus T squared and plus 1. So we can actually approximate, so the Y prime T can be approximate, so the Y by Ti, this is the Y derivative evaluated at the Ti, the notable Ti, and it's approximated by the Wi. So Wi is the approximations value we already got for the YTI. And minus, there's no approximation here, the Ti, the T value, because these are the notables, and then Ti squared and then plus 1. So which means that we are going to approximate the derivative at the Ti by using the values we get from the Taylor's method, Wi, and then minus the Ti squared plus 1. Which means that, okay, originally this one, it should be the Y prime 1.2, and it's approximated by the Wi. The Wi here, it should be the W1.2. This is the W1.2. The W at the 1.2 point. This is the 1.2. And we are going to approximate this one, the derivative with 1319134A, and then minus a Ti is 1.2 at this point, and then plus 1. And this one equals to 2.739964. And this is the first divided difference here. And we are going to do the same things for the Y prime 2. So this is the things in the middle, and then the things in the middle, Y prime 1.4 here. And then we are going to do the same things. And this is at the time interval when the Ti equals to the 1.2, and this is one thing. And then we can do the plug in, and then for the Ti equals to 1.4, and it equals to 3.714865, and then minus 1.4 squared, and then plus 1. And this value equals to the 2.771243321 here. And so we can fill in the table here again. And this one is the number we have. And for the things in between, and then we use the finite difference formula, and it is just the W1.4 value minus the W1.2 value, and then divided the time difference here, and it equals to 2.762345. And by using these tables, and then you can finish all the columns here. This is the first divided difference, and then you can proceed the same things as you learned in the 104B, 104A, and then you can finish the second column, the second divided difference here. And then, so this is the difference between these two. And then the diameter should be 1.4 divided minus 1.2 here. Let me see. Yes, and here doing the finite difference here, and then you would get the values throughout the table here. 0.505 and then 480. And this is the third divided difference from the tables for the table. And then this one, it should be the negative 0.0330 and then 71225. And as you get this table, and then the things you need to do is just collect all this first component in the columns, and then to get their Hermite's polynomial here. So the things you need to do is to write out the table and then fill out the coefficients for this formula, and that is what you need to do to get the Hermite's polynomial. And once you get the polynomial, and then you plug in the x into the polynomial, and then that is the things you need to do to get the approximations values at the y equals to 1.25. Any question here? This is just something based on the 104A. And once you get the polynomial, and then once we get these tables, and then we are almost there to get the polynomial. And let's see. So maybe some of the people here just get confused how to get these tables to that polynomial. So I would just be more specific here. I guess some of people just get confused how to get the polynomial. So I also have the formula below, and then I also have the tables at hand here. And as we can see here, the YT, this is the polynomial. I'm going to just follow the Hermite polynomial below. But here, this is the YT approximation, and FZ0. And then this is the first component. This is the FZ0. And this one is corresponding to the first column, this column, and then the first component here. And this is the 319 things here. 319134A. And for their cumulative sum here, and then when k equals to 1. And so that is the FZ0 and then Z1 here, and then which means that this one is corresponding to the one we have in this column, and then this is the first divided difference, and then the first elements in this column. And so we have, so for the k equals to 1, and then we have the first value in the first divided difference. And for the polynomial here, we have x minus z0, because the things we want here in the polynomial is k equals to 1, and then 2 So the polynomial here, the expressions ends at k minus 1 and then k equals 1, which means that the expressions ends at z0. So here we have for the first expressions, first we focus on the values at the first divided difference column, and then we got 2.713994. And for the polynomial here, we just need the first point, and this is our z0. Let's see. So this one is z0, and this is z1, and then this is z2. This is zv, corresponding to the table below here. So for the first one, we just need to write down the expressions up to the z0. So the z0 here is just 1.2, and this is the k equals to 1 case in the sigma sums. And then what about the k equals to 2? K equals to 2, and then we focus on what we have here, and that is the second divided difference formula, second divided difference tables here, column here, and then we focus on the first component here, and then the coefficients for this part should be the values we have here. And so we got the coefficient, and that is the coefficient point 1111885, and the expressions, the polynomial expressions here, and then it should be starting from the z0 to, because k equals to 2 here, and then we should write up to the z2 minus 1, that is z1. So we got, what we get here is the t minus z0. z0 is the 1.2, and the z1 is t minus 1.2 as well. So this is because z0 is 1.2, and then z1 is 1.2 again. So we have t minus 1.2 and then square. And let's see how many items we need to do to write down here, because in this examples we are doing the cubic one. The cubic, actually we are doing the cubic Ermites, and which means that we want up to the n equals to 1, so that the here k equals to 1, and we actually want the n equals to 1 here, and then so that this one, the order here is 3. So that is the cubic Ermite polynomial. And but we just persist to k equals to 2, and we need to persist to the number here up to the 3. So there's one more item here, that is the k equals to the n equals to the k equals to 3. And what about the k equals to 3 here? And then we go to the last column. The last column here, and then that's the third divided difference, and then it's corresponding to the k equals to 3 item. And this is the coefficients corresponding to here, coefficients, and then we write down the number. And the numbers we have here is G negative 0.3014275. And for the number, for the polynomial expressions here, we actually have 3 expressions, t minus, t minus, t minus. And as you can see here, k equals to 3, which means that the expression here is starting from z0 and then but ends at z2, because k equals to 3 here. 3 minus 1 is just 2. And so we just look at the table, and what you see, all the points here, z0 is corresponding to 1.2, z1 here, and then this is z2, and then we have the 1.4. So what we have in this expression is t minus 1.2, t minus 1.2, and this is t minus 1.4. And this is the whole things, and this is the Ermine polynomial. And once you get the polynomials at hand here, and you can get any numbers, the approximations to any time in between the 1.2 and 1.4. So this is specific for the 2 points. This is the interpolations between the 1.2 and 1.4 value. But this is not for the 1.4 or 1.6. This is only for the 1.2 and 1.4 interval only. Any question here? So what you need to do is just compare the table you have, and then write down the table, and then compare the formulas here, and then write down the items one by one. And all these coefficients are the first components in each column, except for the this z column. We have the this is called a zero divided difference. This is first divided difference, second divided difference, and each column is corresponding to k equals to 1, k equals 2, k equals to 3, and this is the things. And this is only for the interpolations between the t equals to 1.2 and t equals to 1.4. And if you want to interpolate the values in between the 1.4 and 1.6, then you need to rewrite your interpolations polynomial again. Does it make sense? Okay, this is the things. This is a part I left out last time, and this time I am going to go back to what we are currently working on. And we are working on the things about the Runge-Kutta methods. And last time I mentioned that why do we need the Runge-Kutta methods? Because some people just don't want to calculate the derivative for the f, because in the Taylor's methods, you need to calculate the derivative of the f regarding to the y variable. And this is what you need to do when you're creating the formula for the Taylor's method. But for the Runge-Kutta methods, you need to evaluate the f function at different points. And you can see the pros and cons here. The pros is that we don't need to calculate the derivative of the f function anymore. But the thing is that the computational cost comes with the evaluations for the f at different points. And you can see the Runge-Kutta order 3 is quite complicated. We need to evaluate at the f function 3 times. The f function here, and then the f function here, and then the f function here. Oh, there's one. Oh, only 3 times, because this one is the same as this one. We need to evaluate the f functions 3 times, and then for the Runge-Kutta methods order 4, actually we need to evaluate the f functions 4 times, 1 time, 2 times, 3 times, 4 times. And so there's the pros cons here, and let's see. This is Runge-Kutta methods, and I will come back to here later on. And for the order here, which means that I mean the order 3, and then it is about the truncations error, the local truncations error. And for the order 2, we have the local truncations error, locitus h to the order 2. This one has a local truncation error as the h to the order 3. And I'll come back to here later on. And then, but here, we want to mention one more things about the methods we can use to calculate the linear system, the initial value problems. So as you can see here, we are using the f functions value. But if you take a look at the value, we evaluate the value f here, but what about the informations we use for the solutions, the approximations to the solutions? We just need the previous steps approximation here, right? Just one step before the I+1. And we just need one step. Approximations we already know. And so people just think about, okay, actually we have already calculated the W0, W1, W2 up to the WI. And what about we use some informations we already know? We already know the W0 to WI, and then what about using the informations before it? And that is, so this kind of method, including the Taylor's method, including the Euler's method, and Runge-Kuttel's methods, we just need the one step prior to our current set, the informations here. We just need one. And these are called one-step methods. And people just saying, what about multi-step? We use WI, WI minus 1, WI minus 2 informations to calculate the WI plus 1. This is the multi-step methods. I'm going to skip the derivations at this moment because it's complicated. And let's see the multi-steps methods. Let's just get all the idea about how to solve the initial value problem first. This is the multi-step methods. Multi-step methods for the IVP problem. And I will just give you the formula first, and then just get the taste, and then to know what is going on for this methods. So for the multi-step methods, I'm going to give you two typical example here, and you would just compare what we have and in the Runge-Kuttel methods and Taylor's methods. And two typical methods are so there's a name for them. And once again, the fourth order here, it represents the truncations error we have. The fourth order, and there's a name here, Adam Bashforth technique. And these are typical, these are two typical methods. And then actually you have 2 order, 3 order, a 3rd order, 5th order, and so on and so forth. So let's say we already have the first several steps information. And so we are still divided the interval, the time interval into, this is the time interval A to B. And then we are divided the interval into the T0 and then T1, T2, M to the Tn. So which means that, okay, we want to approximate the values at the node points T0, T1, T2, Tn, and then we want to calculate the approximation for them, the Y value at all these node points. And let's say we already get the several steps value, and then that is the initial steps, the initial point, the initial time point. And then we also get the W1. W1 is the approximations to the, so this one is the approximation or the exact values at the YT1. This is the approximations of it, or the exact value. So let's say we get some information about the points at the very first few point. And let's say we also have the W2 value and we have the W3 value. And all this can be the approximations at the Y2, and this could be the approximation at the Y equals to the value at the time 3, the T3 node device. And this methods, this typical multi-step methods, and then the formula looks like below this, the below formula, WI plus 1, and it's updated by the previous 4-step value. And so the first one is WI. It is still WI. This is one step before the I plus 1. But the things after it is the H over 24, M, 55, and the F, TIWI. This one is still using the one step before the I+1, but the next item you will see we are using more informations, more prior informations, and then you will see WI -1 here, plus the 37, and then FTI -2, and WI -2, and I need more space here. Minus, and then FTI -3, WI -3 here, and this is the evaluations, and then there's square brackets N here. So as you can see, we have a lot of evaluations of the F function as well, but this compared to the Runge-Kutta methods, we are using all these values again and again. So let's see on the line here, and actually you will see this is the W0, W1, W2, W3, and so which means that the W4 is based on what we have calculated before. The F function evaluate at all these points. And what about the W5? If we want to calculate the W5, and it's based on the points, it's based on, so let's see, 1, 2, 3, 4. So it's based on the 1, 2, 3, 4 points before it. So if you take a look at this colored part here, so these are the blue parts is the things we need to calculate the W4, and the green part is the things we need. This 1, 2, 3, 4 points. These are the 4 points values we need to calculate the W5. You can see we are reusing the W1, W2, W3 value here. The F function evaluate at these 3 points here. We are reusing some things we calculate, and this is not like the Runge-Kutta methods. If you take a look at the Runge-Kutta's formula, and we just use the F function's values one time, and then the next iteration we drop it. We don't use it anymore. But here the F function evaluate all these points. We are going to reuse it again and again. So, which means that we have a less computational cost compared to the Runge-Kutta's methods, and this is the benefit. And another benefit is that you already see some phenomenon in the errors of the propagations errors in the IVP problem. So which I'm saying that, so for the error at this point, the error at this point and the error at the end point, you will see the error is increasing if we use the Taylor's method, if we use the Runge-Kutta's methods, and you will see the error is increasing, right? And which means that at the early stage, the error is smaller, right? So if we use some data is from the early stage, and then we probably get a more precise approximation because the data from the early stage is more accurate. And then when the time propagates, and the error will become larger and larger. So this is the idea for the multi-step methods. Use some data that is from the prior knowledge. So prior knowledge, which means that we have already calculated the W0 to the WI, and we use the data we have already calculated. And this is one type of the methods. And there's one more typical method here. There is already 8:50, so I can answer your question. We have Wednesday class, and we need to finish all the things about the multi-steps next time. And I will just write down the things here: fourth orders, Adams, Moulton's methods. And we'll finish this part next week. And next Wednesday, not next week, sorry. Next week is the final exam week. And I will finish this part on Wednesday and then no class on Friday. And if you have questions about the reading, please come to my office hours as soon as possible. Don't miss your opportunity.不是周五，应该周四就发了。
然后周四就发，然后之前可以看一看，然后问问书上的问题，然后周五就是周四之后就是。
哦，我应该是周四晚上发，但是就是说，就书上的问题是不能，就是发了他们就不能问了。对。
我忘了为什么。作业。啊。我 next 6我看到你会问。